All right, this is AP Podcast 7.5, and we're going to talk about the common ion effect. So this is the definition of what it is. It's just the shift in equilibrium that's due to adding an ion that's already involved in the equilibrium. So for example, if we were thinking about acetic acid, and we know acetic acid is a weak acid, so it dissociates to some point to produce H plus and acetate ions. If we were to add more acetate ions to this, this would be the common ion effect. So we're adding an ion that's already there. We could add more hydrogen ion as well. But what we're looking to do is what is the effect on the percent dissociation? So how does that affect how much of this is dissociated? And also we want to see how does this affect the pH in certain situations. All right, the common ion effect is an application of Le Chatelier's principle, which is what we talked about before. So we're stressing this equilibrium system and it has to come to a new equilibrium. In general, though, it's going to reverse the dissociation of the acid or the base, whatever we're looking at. It's going to cause less of what we have to dissociate because there's already an ion there. It's going to shift the equilibrium to the left. It's also going to lower the percent dissociation. So, our example of what we're going to look at here, it says, what happens when ammonium chloride is added to a solution of ammonia? So the first thing we're going to do is, if we have ammonium chloride, we know this is a salt, we're going to figure out what this splits into. So ammonium chloride, if I put it into water, is going to split into ammonium ions and chloride ions. And then the next thing we want to talk about is, well, we have this solution of ammonia. So let's look quickly at what ammonia does when it's in water. Ammonia is a weak base, so it's going to accept a hydrogen from the water. So we're going to end up with ammonium ions and hydroxide ions. So this is the salt that we added in to this equilibrium. And what we can see is that the ammonium ion is the ion that's already in this equilibrium expression, this equilibrium equation. So what we're doing is we're adding more ammonium. And according to Le Chatelier's principle, if I add more of this, the equilibrium should shift back to the left in order to account for that stress that I've added to the system. So in this case, the equilibrium will shift to the left. And what that's going to do is it's going to lower the amount of ammonia that actually dissociates. So you're going to have a percent dissociation that's smaller than what you would expect. All right, we're going to do one practice problem together, and there's two parts. The first part is wanting us to calculate the percent dissociation in pH of a 0.1 molar solution of acetic acid. And the second part wants us to do the same thing, but it's giving us a mixture with acetic acid, and then we're adding in some sodium acetate. So we're going to start with part A. This is just finding the pH and the percent dissociation of a weak acid. So this is nothing new. We've done this. We're going to use an ice table. Acetic acid, I already wrote on here once. That will dissociate into H plus and the acetate ions. And then if I have my ice table, so initially this is 0.1 molar. I have none of this and none of that. We have our minus x and our plus x's, and then our equilibrium values. They give us the Ka, so Ka is equal to, in this case it's 1.8 times 10 to the negative fifth, and that's equal to x squared over 0.1. And I am going to ignore the minus x like we always do. So what I'm going to find out is that x is equal to, and once we do all that math, 1.3 times 10 to the negative third molar. And x in this case is also equal to the H plus. So we need to calculate the percent dissociation and the pH. So I'm going to start with pH. pH is just the negative log of x, that H plus that we found, so 1.3 times 10 to the negative third. And when I plug in that, I find a pH of 2.89. And that makes sense. I'm dealing with an acid. The other thing they wanted us to do was figure out the percent dissociation. And remember, when we do percent dissociation, we take the value of X, however much dissociated, and we divide it by the original concentration and then multiply by 100. So when I do that, multiply by 100, I'm going to get a percent dissociation of 1.3%. So those are the two values, and we want to write those down and keep them because we're going to compare it now. If we add a salt to this solution, how does that affect the pH, and how is that going to affect the percent dissociation? So that was part A. That should look very familiar to you. The second thing then is our mixture that has acetic acid, still the same concentration, but now we have 0.1 molar sodium acetate with it. So what we're going to think about for a second is if I add 0.1 molar sodium acetate, this thing is going to dissociate into 0.1 molar sodium ions, and it's also going to dissociate into 0.1 molar of the acetate ions. And I know that the sodium ions are not going to affect what I have going on here. It's the acetate that I care about because the acetate ion is the common ion in this case. So I need to remember this when I go to do my ice table. I'm going to start the problem the same way as I did part A. I'm going to take the acetic acid and write its equilibrium expression here. So I have acetic acid breaking into H plus and the acetate ion. Then I make my ice table. What's different about this though is the acetic acid's initial concentration is still 0.10. I still don't have any H plus, but now I have 0.10 molar of the acetate ion, and that's something I didn't have before. So now instead of this being 0, it's going to be 0.1 because that salt that we added is adding this common ion to our equilibrium expression that we have going on. So still minus X, plus X, and plus X. Still some of this is going to break up and produce some hydrogen ions. And then we have 0.01 minus X, X, and then 0.10 plus X. And then I take this, I'm going to use the Ka again. I want to solve for what is this X value right here. So this is going to be X times, and I'm going to ignore the plus X here and the minus X there. It's not going to affect the calculation, the answer, and it makes our calculation a whole lot easier. And that's 1.8 times 10 to the negative fifth. So when I look at this, both of those conveniently cancel out, and what I'm left with is X is equal to 1.8 times 10 to the negative fifth molar. So already, if you look back at that other problem, the value of X that we got in part A without the common ion was 1.3 times 10 to the negative third. We can already see that our concentration of hydrogen ion that we're going to produce is quite a bit smaller than what it was when we've added this common ion into the equation. So moving on with this, the pH. The pH of this, if I took the negative log of 1.8 times 10 to the negative fifth, I'd end up with 4.74. So I should get a higher pH because I produced a smaller concentration of H+. And then also the percent dissociation, I take the 1.8 times 10 to the negative fifth on top this time, still divided by my original concentration of 0.1 times 100, and my percent this time is going to end up as 0.018%. And looking back at part A, we can see that part A, it was 1.3%. So adding this common ion really shifted the equilibrium back to this side. It didn't allow as much of the acetic acid to ionize as it normally would. And that's what you should expect, and that's what you should see with these common ion problems. All right, that's all we're going to do together with the common ion. This comes into play when we talk about buffers next, but for now, that's kind of a quick introduction to what a common ion does to an equilibrium.